science as far as like optical systems, like different, like in biology, maybe you measure the spectrum wavelength of something like a UV visible spectrum. I don't know if you've done that at all.
Not really.
No. So typically, like you'll measure like the absorbance profile of DNA or a protein or whatever, and you get these really broad absorption bands over like 100 nanometers. The thing is when we do elemental analysis like this, we get what we call lines. These are extremely sharp. We're looking at the wavelength as far as nanometers, 324.752, so that means we're going down to the thousandth of a nanometer. That's the resolution now, a thousandth. I think Scott can appreciate a thousandth of a nanometer.
Yeah,
that's pretty small.
that's pretty small.
That's the resolution our spectrometer has here. So, anyways, what you get is off that plasma, there's literally thousands and thousands of emissions lines, but very few of them overlap because of how sharp the lines are. The emissions happen between 180 nanometers, maybe up to 700 nanometers or so, to over maybe, maybe over 500 nanometers is what we're looking for emissions at. And if we can get resolution down to even 100th of a nanometer, you can literally theoretically see like 50,000, 100,000 different lines there, and not a lot of them overlap. So you don't get much for interferences. And what you'll see here is like this is an emission line of something else, and I don't know what it is. I mean, it could be any element. This is the emission line specifically of copper, but they're resolved, they're separated. So as long as they're separated, we just focus specifically in this case on the copper, and we can quantitate from there. This one's at 259 point something for iron, for potassium, magnesium, zinc, chromium, whatever. That's just what's in this method.